Okay, good morning, everyone. So today we will, I already sent you an email with a new update for our tool. So, and there is two files, we will use it today. One is just an extension for the last one that we already did together. And the new one is one of the first machine learning algorithm that you will start with today. So we will start just in the beginning, make a kind of a quick scan about some of the important terms and definitions that we need to highlight before the start of this technical steps. And at the end of this today, we will at the end of today we will see each one this kind of feature table that I asked last time. I hope that you manage to do this, and maybe we can find some interesting features that maybe we need to think about how to do it for each one. So for the start, this is usually I start from this map. So today we will cover these red terms, from distance functions, the probabilities, what's feature engineering, and we will start with the first machine learning algorithm called KNN. It's one of the very famous and basic, well-known machine learning algorithms. So before we start with this machine learning, we need to highlight what is this probability, and there is some probability concepts. We will not go into too much depth about the calculations of these probabilities or these algorithms, but we need to define kind of some anchor points to know and to get a little bit of stability between these terms. So with the probability concept, most of us already know this kind of ideas in high school or maybe in middle school, how to ask about the probability of getting this kind of a dice or a dime that you throw it, and you want to know what's the probability of getting one of these faces, or two or three, 1, 3, 5, and so on. And usually it's this kind of ratio, this kind of relation. So when you say ratio, this means that you establish a relation. And maybe later you will find that this kind of ratios, you can establish it between features. So you have a kind of a number of requested outcome and the number of total outcomes. So you have to, if you want to say what is the probability of getting 1 from throwing this from this dice, so let's say 1 over 6. If you want to ask about what's the probability of getting 1 or 3 or 1, so then it's you add these probabilities together. So it's a 2 out of 6. And one of these important that you know what is the size of your sample space. So we will face this kind of problems in machine learning that to count what is the number of total outcomes. It's like that you ask, if you will design a space, how many probabilities or no, how many examples you can develop. So for these tools, usually some people, when they finish this machine learning examples, they think that this is enough. You draw a couple of designs, or you collect some designs from online, or you collect some comments from, let's say from Facebook, from Twitter, and you think, maybe this is enough. So how to know that this is an enough amount for your requested outcome in the future? So this is one of the questions that you need to know before you start. Is this enough for what I need or not? Because what machine learning algorithm at the end will give you, it's something in between. It's interpolate between your data. It will not be able to extrapolate. Then so this is one of the examples, this kind of floor plans. And now you have, let's say, you have a new floor plan and you want design. And you have this kind of, let's say, this is a 30 floor plan. It's a few amounts. And you start to add some features. So let's say some of them has, let's say the first feature is the cost. It's maybe one number represent something meaningful for you, that this is a cheap or a moderate or expensive floor plan design. And maybe this one number comes from kind of functions that you developed, maybe something related to materials, to the wall areas, some of the building services. You can add a lot. So maybe it's one number, but it to develop this number, you have to do a lot of functions, sequential functions to get to one number. But for you, it's one number is let's say is enough. Let's say this kind of a cluster, I know I developed this design, and this is for economy, and this is for moderate and for expensive. So if you only have 30 floor plan, so then if you think with the older idea of our probability that you know from this high school, so then if what's the relation of your new request of a new floor plan within these data? So then your request is, let's say, 1.3 probability to get an economy floor plan, or 0.4 for moderate, and so on for expensive. So this is the relation to the whole of what you have, but not for all of the floor plans possibilities. This is, of course, endless solutions. Then maybe you need to add something else. You need a kind of a subclustering. You will add new features, and with adding new features, it's like that you adding kind of different faces for the context around you. So this will make a kind of a new complexity. So let's say now, and maybe for this economy cluster, some of them has different maybe areas. So the new feature is the area. I would like to explain this kind of the area, which is, let's say, for regular shapes, it's only the multiplication of two numbers, the length and width, and this is easy. But if for irregular shape, it takes much more calculations and sub-relations to finish to return out one number. And you can add more. You can add more to explain in detail this kind of features that you would like to add. And if you added more and more, this increases the complexity of your design or for your navigation, because you need at the end, let's say, maybe ask one single question. Maybe at the end you need to one or two parameters. So how you get balance between all of these weights for each feature. So maybe at the end, this is the last question. Maybe it's a new design for a floor plan, or you ask for this new design, is it acceptable or not acceptable? Maybe it's we call it later. We will see that if it's just a kind of a class, the end question is a class of accepted or not accepted, or others accepted and not accepted need to be reviewed. Maybe you can add different kind of classes, or you want to redesign. So you wanted a new design from these tools, and each of these target is important that you know from the beginning, because this will This will tell you how to balance, or what kind of algorithms that you can use later to find your results. So if you wanted to generate models, this is one of the this is one way. And if you want just to cluster, or you want to get a kind of a binary output, so yes or no, all of these kind of target is usually is an important before the learning process that we will use in machine learning. So it's mainly it's a question of weights. It's mostly you have the data, and mostly you have features. Sometimes these features is incomplete, but mostly they are, let's say, complete features. And you need to know what kind of weights should I establish for each of these features in order to get a target. So this kind of three terms, just for me, it's a kind of an analogy that for the context and features, it's almost within the data. And the situation, which means that you are the subject and you look into this data, and you need to figure out what kind of situation. And you need to balance these weights, that all of these features in the context, maybe you need to highlight some of these features, and some of them you don't want to see it at all. So for this, there is another concept within these kind of weights. There is another analogy that you can think about weights. It's a kind of a distance. And this is one of the first ideas that we will develop together this time and maybe the next time, about how to look at for weights as distances. So usually we know this kind of non-Pythagorean theorem, and how to calculate the Euclidean distance between 2 points. It's easy. This is x and y, and you have to subtract between this end point and this starting point. So this is you get the square plus the square of this, and then you can get the square root in order to get the clear Euclidean distance, or you can use it also as a squared, as you like. So this is one. And from the next time we will get introduced to other distances. So, and this is one of the generic way of distances that all of the machine learning algorithms use, but mostly. But it's my point of view. It depends mainly on what kind of features you have and their complexity. Then you can use different kind of distances. So for this, you will get the square root, and they say, if this is my new feature and this is one of the data, and I need to know is this close to this one or not? What's the distance between them? So then you need to make this kind of a subtraction between each feature. Let's say it's like rows and columns. The row is for each of these data inputs, and the columns is these kind of values of features. And maybe each one of these features, maybe you need to develop a tool for it. Sometimes it's one feature, but you need a kind of a simulator to do it, a parametric tool to do one single function. One single feature. And before we start about what is this kind of terms, this is a kind of a brief, because we need to highlight our approach. So with machine learning, if you don't have a data, so you are not there. you need to start from the data. It's not like the parametric functions or parametric modeling that you start from parameters and establish a sequential process. With this, no, you are in the inductive process, so you have to get a data. So this is the first question. The question: do you have a data or not? And maybe if it's not complete or it's few, then we discuss is it enough or not. But mainly you have to start with, even if they are few, maybe you can have tens or hundreds, just a few, just to start to navigate. Then we will find how to decide is this is enough or not, or what kind of a new data that I should add. So this machine learning, it's kind of a set of algorithms that can extract this kind of 4 dominant approaches for using machine learning to extract the patterns from data. So if there is no patterns in data, so then you don't need machine learning. Usually it's for extracting patterns. Then to use these patterns usually is to predict future. Something like what I showed you in the first lecture about this, let's say, airflow, that you would like to predict a performance of something, or you want to predict if you posted one of the images on the web on any of these online Twitter or Facebook, what kind of comments should I receive? It's kind of a prediction, and you decide this based on what you get. So it's very important that you highlight this, that this is the output according to the limitations of data. So you have to know exactly what's the limitation of your data. Then the third thing is maybe to emulate a similar behavior. So let's say with this floor plan, it's very hard that you try to think that I will emulate the thinking of the human. And for me, I think this is not the case that we discuss in this course. That now we need to find a kind of to navigate between our ideas, and maybe if the machine learning is able to show us something in between, but it's not about to replace the human thinking. Or to perform a kind of a decision making, but this should be very clear. It's under uncertainty. You are not certain from anything, and that's why usually you should say at the end, what is the probability of your result or your decision? And this learning algorithm, you will find this kind of term. It's used a lot, learning, and you shouldn't think about it similar to humans. It's completely different than humans. Okay, but according to, let's say, this the analogy that the computer scientists in the past tried to develop these kind of algorithms with a kind of a metaphor from the human, how they learn. But it's mainly this kind of 3 terms that you will find: learning algorithm, or training, or learning rules. And mainly it's just a kind of a steps and the procedures. And this kind of procedures is to modify or to estimate the weights and distance. So you'll find that mostly this is the questions. It's how to modify or how to balance these kind of weights in response to the target that you would like to achieve. And usually I say these 2 terms. You can maybe you need to some algorithms to modify or to estimate, or you can say that this is the weights or distances. So these kind of different meanings. It's for me, we will develop it later, and it's important that you see different kind of perspectives for the same algorithms and tools that you use. And this kind of weights and distances, it's between original data elements. So maybe you try to navigate within your data, and you would like to establish these kind of distances, to know which one of these, let's say, floor plans or images or comments from Twitter that, yeah, this is near to what comment, or between the data elements and your testing elements. This is the last idea, but this is, we will be explain it from the next time when we will talk about a sub-kind of algorithms inside machine learning called neural network or artificial neural network. So then we will find that, yeah, these weights and distances is between kind of units. They call it neurons. So this is from the next time. And just briefly and simply, without going into too much details, that usually machine learning algorithms, you should look onto this mainly two things: to the target or to the learning, or let's say this is kind of the procedures of updating the weights. So if you look into the target, you will find these kind of terms: regression, classification, or clustering. And I mentioned this within the last slide. Let's say regression and classification. This means, let's say here, if the output of your question that this is acceptable or not acceptable, this is a kind of a classification question that you would like to find kind of a class at the end, or maybe the last question is something. This is economy or moderate or expensive. Maybe this is your end question. And by that you establish a kind of a classes. For regression, this means that you need something in between. You have a kind of a usually with the continuous data. So let's say with this airflow. So maybe I need to make this kind of regression that you have a kind of a continuous data for the movement of this airflow, and you want to generate something in between. So your data almost is continuous. With clustering, it's different. That you need to establish these kind of classes or clusters, and sometimes with the hierarchical clustering, that you would like to find a kind of an overview for some amounts, and then a kind of a subdivision of sub-regions or sub-views. So these are the main idea about the target. For the learning process, there is many learning strategies, but mainly it's supervised and supervised. You will find also online there is a semi-supervised, or there is a reinforcement learning. But for this course, I think it's enough that we will mainly look at these main two kinds of learning. For the supervised learning, this means that your target is clear in your data. And usually we say this it's like the labels. So in this example, this means that you should also for each of these floor plans tell me that it's at least it's acceptable, or something in between. Tell me the class, if it's acceptable or not, or you only tell me that, yeah, that this is acceptable. So if it's and there is a kind of a threshold, you have to identify a threshold that, yeah, this is not acceptable. And also you can find this kind of a classes that, no, if maybe the last question is economy or moderate or expensive. So this means that you need to highlight this class, that this is economy or moderate or expensive for each one. This is me that is supervised. With the supervised, it's a clear path from the data to a label or these classes. For the unsupervised, usually you don't have a label data. If you have label data, you can also train with it, but it's not the target to find a clear identity for each one. It's just you try to collect and cluster your data, maybe to visualize it. Then it's like that you have, let's say, hundreds or thousands of these floor plans or images, and you would like to discuss or navigate in each similar classes. And usually with this question is sometimes you need a kind of a representative. Let's say this image represent other images. This comment of Twitter represent other comments. This kind of analogy of clustering can be used and very helpful. And we for today we will start with this one of the well-known machine learning algorithms called KNN. This is a supervised learning, and we will use the supervised learning today for a kind of a classification problem. From the next time, we will use one of the unsupervised learning algorithm for clustering, and we will see how can we use it for for other. It's one supervised learning algorithms, but we can address different kind of targets, but mainly it's about clustering. This we will for memorization pattern classification we will start with it from the next time with the unsupervised learning. Just to be sure. Yes. Okay. So you should, after you download the files, you will find one 3DM file called this 27, 1 and 2. And there is two grasshopper files, one called 27.1 send, and you will find this 1 and 2. So, and this is what we will explain today. And from today, we will not go into details of creating these kind of components, too much details. That now we will share. I will share with you this kind of almost a clear algorithm, and we will discuss it. So we will not build one by one, but we will focus on discussing the inputs and the outputs. This is the main target from today. So in the last time, we did all of these, no, not the white color, this kind of color for these parts, and with the white groups, it's the new thing that I added. So for this part, if you remember last time, we you have this only these 4 floor plans, which is very few. I will hide these points. Okay. And I think, yeah, so I also will hide this part. Okay. If you remember last time that we have this kind of question and this kind of floor plans, and I would like to know what is the nearest floor plan. I think this was the last question, and this was connected to this bounding box, because my question was only based on the this is height and height, about this kind of length and width for the whole floor plan. And today, just I added this small components just to make this kind of floor plan more dynamic, and to see its projection, this kind of points that represent the X and Y from the origin point. And this X and Y is for this floor plan. So let's say it's like this. So now I will hide this. So what we have here, now I added the 1 point somewhere, and I saved it here. I said this internalize data. Usually we use this set 1 point from Rhino, and then if you want this component to save it, then you make this internalize, and this is the rectangular shape, and you just need this kind of shape to navigate. This is what I told you last time. What if we make kind of a more dynamic interface? And this is a 2D slider. You can find, I think it's a 2D slider. Sorry, this MD slider, I think. This is a multi-dimensional slider. And with this, you can make a double click, and you can highlight this this X domain. You want, let's say, the floor plan X and Y from 8 to 20, or from 8 to 20 to this for the length and width. So this is the maximum is 20 and 20. So the result is a point, and I don't need it as a point. I need to deconstruct it to make this kind of rectangle. And actually, maybe also I don't need this. I need this, yeah, maybe just to view the output, but mainly you only need these two, and you can connect these X and Y with these points. So, okay, so this is mainly, but let's say that. So this kind of dynamic thing, maybe you just will give you how you navigate as a projection, and how you get the results of these floor plans. And the other steps is the same. You have a kind of data. You build it like a groups. You deconstruct into kind of shapes, and these sub-shapes you need to read a distance. This is the Euclidean distance only between points. And after this, we started to sort to know what is the nearest distance, or what is the farthest distance, and to get an index. Then the last thing is just a representation, just to move or to make this kind of text and so on. So what's new just here? Okay. Last time we used this this kind of text. Okay, we didn't make it good or more clear or rich, but just a few text. And then we used this word vector. With this word vector, usually just take care that the output of this word vector is the list is flattened for all of the inputs. Let's say now we have 4 inputs, and usually you need to call this partition. Yes, maybe someone asked me last time, not icons. I'm not sure if this is helpful or not, but it will be helpful for some of you, especially if you are as a beginner in Grasshopper. So you need to call this partition list with a lot of the output of these tools that I developed for this course. So you need to the list, and you need to partition it. So this partition this into 4 branches, and with these vectors. So sometimes you need to join this as a text. It's text join with this semicolon, maybe just to view it if you need. Or there is some tools I developed for this course. It needs the vectors to be represented as a text like this, not as numbers like this. And we will see what kind of tools need this or that. Just you need to to know why we need this in the next time. And this is just a kind of a representation. So now these are the text that we have after you filter it. I think we removed the 2 and the comma, but we didn't remove the connected. So the word connected should be here. I think they are 7. This is 6. And I have another tool I added this time. We'll find it in the next file that can return out and clean all of the words and tell you this kind of the label of these features. So if you try to flip this kind of flipping the matrix, with the flipping the matrix, you try to get the first element. Let's say it's the entrance. You need to see all of the entrances. Okay, or let's say the word connected. So the word connected, how many times it's represented in each of these lists. So this is just to flip. And sometimes you need to see also this kind of distribution. Okay, it's something basic. In some tools it calls a histogram, or you just kind of make a kind of a list plot. So with this kind of plot, it tells you that for this entrance, if you would like to see how many times it is represented in your data, and what kind of weights do you have for this data. So let's say this is the entrance. This is the second one. This is the, let's say, the word connected, and this is the hallway, and this is the reception, and so on. And maybe with this you start to find, okay, this has a higher weight, and then you can discuss, is it really needed or not? Because maybe you can say analyze one of the comments on Twitter or on Facebook. And then this kind of comments maybe has some repetitive words, not just these kind of stopping words that like the or and, or these kind of words. No, there is, yeah, maybe some informal words that maybe it means something or nothing. And then you discuss this from your subjective points. Do I need these points, these kind of features or not? Because they are a lot, and they are also, you need to get this and see its kind the distribution of this feature alone, not with the others. Then to discuss if we need to remove it or not. So then let's say maybe I need to remove, with this word remover, you highlight a specific one that you need to remove. Okay, so you should do this with almost all of your data, just to know kind of a distribution, an overview distribution for all. For this part, okay, so this was the point. These are the points that projected from the X and Y for each one. And this is just for kind of a representation. I think it will be helpful just to see, and maybe it gives you kind of idea that maybe each of these points, what kind of features and what it represents. So you can follow this kind of algorithms, just a representation. You have a point, you have a line, the line in the Z vector. I divided according to how many are the features, and I added the text tag with each point. And then now this is one of the complexity that at the moment we only represent the each of these floor plans only with the length and width, and the others it's just for us. We still didn't use the other features. Okay, and this is just for yeah, this is for the text. Yeah, this is the tool that I just mentioned. Display just icons. It's called a word cleaner. So this delete the duplicated word. You just so this was the words. Okay, they are duplicated. So actually this instead of this one. Okay, this is I did it manually, and this is automatically. Okay. The other idea, maybe you can find it with this Excel sheet. Already there is a CSV file, okay, called the feature table, CSV. You can double click here, ask for path, this file path. And with this file path, you can choose from your computer what is the path of the file that you would like to read. Then this is a read file. This is one of the Grasshopper components. And the output is just reading it line by line. You can open this file with the Excel sheet. You can write with an Excel sheet. So this should be kind of the overall vision. Maybe, of course, it's more complex for big data and more complex projects, but yeah, with our examples, this is enough to discuss. So here, let's say the proposal is this is the index that you will mention, or the name. You can call it as a name. So this is proposal 0, 1, 2, 3, 4, and so on. And these are the features. And maybe there is a kind of a description. Let's say I call this is view high, cost low, view high, cost low, or and so on. This is the 0 class. And this is 1 class, and this is 2 class. Maybe this is an economy and moderate, and maybe something maybe expensive, and so on. So it's so for at the moment we do not discuss what is this class really and what is this represent. It's maybe one number have a meaning in for you as an architect or a designer. And usually after you select these paths and read it, you need to split this with column. This is called the text split. And you add the text that you would like to split, which is this comma. And this is the output. Because maybe you have a kind of a data. Okay. And if you would like to not to flatten it, so you can read this per line. Then it's automatically will be grafted. So now we have 9 branches. And in each of these branches, you have this kind of data. So the first branch is just the titles. Okay. Then from the second one, this is say this is the first alternative. This is the index of the alternatives. This is 0, and then these are the features and the class at the end. So maybe you need to remove this the titles of your table. So you can make cal item or cal index. And the default is maybe you need to set integer 0. So this means that within these lines, I removed the first one. Then I can start to see how to use this. Also to remember this kind of flipping the matrix, if you want to collect, to see all of the indices on one branch. So then use flip matrix. This will collect each of these indices together in one branch. So the first one is the proposal. All of these. This is feature 1, feature 2, and so on. And the last one is the classes. So all of these, just a few components, just to for you, especially as a beginner, you need just to know it in order to use these as an inputs later for our algorithms. This is enough for this file. And then let's start our main topic today. Window. Okay, so you remember now with this file, I only discussed here that just imagine that you have each of these points and you navigate around them. Okay. And these points represent these shapes. And now just imagine, yeah, okay, let's say you have, I will unhide those. Okay, just think that maybe imagine that each of these points represent a design. And you have a kind of a point like this, and which is your question or your new design. And with this new design, you need to know what is the distances. So what we will introduce now this idea of K and N, which means that each point of your new design need to ask or need to measure. Okay, usually I use these two things, measuring and asking. Well, measuring, you need to measure the distances between these points, and this new design says what is the nearest one. Let's say it selected this design, like what we saw here. This was only an output for now. Our discussion here was only, I need only the nearest. It's only one design. And if you remember this, with this sorting, you sort and we select only the first item. But there are others. But here, we will start to discuss something else. I will just change. I get used to use these icons. Okay. So now this is kind of a suggestion. Maybe it depends on your designs. We will see it together at the end of the day. So now I have these 9 points. 1, 2, 3. That's 9 points. These 9 points represent designs in this space, and I represented here the classes. So let's say the first item. Okay. So these are the points. 0, 1, 2, 3, 4, and so on. And according to their sorting, these are the 0 class, this is the 1 class, this is the second class. Okay, so usually here we connect the data. And here we connect, maybe it's 1 point, or maybe it's a lot. Maybe it's a grade of points. It's a, you would like to find a kind of, to see all of the possibilities between these kind of designs. So we will make this a little bit later. Just now we focus only on one single design, and now we move it here like this, not with this dynamic slider that we did before. Okay. So what is the this KNN used? So if we look at these points, they are referenced points. And for KNN as a component, it needs the data to be represented as this way. So I developed it not well, with this kind of a branching numbers. It's with this kind of a text way. It's not regular, and it's not efficient with, especially with complex data or too much data. But it's enough for what we do. So now you need to do it like this, because the problem with the points, it's sometimes it's with these brackets. So I used this word remover, and here you will find that I only added set multiple text. I just removed these 2 brackets. Okay, so then you start to make the inputs. So here is your data. This is X. Y is your question. It's 1 or more. The third input is the type of distance. If you click here and select help, I mentioned here with the method distance, if you choose the 0, this is called the cosine distance method, Hamming distance method, Manhattan, and the third, okay, just Agostino raised hand. I think you can unmute yourself.
Yeah, thanks, Mohammed. I just had like one quick question. Because you sent a new folder yesterday evening, and I installed the components, but for some reason they don't work for me, or they don't appear again in the ribbon. I was just wondering if anybody else had the same issue.
Okay, if someone else have the same issue, please let us know.
I had to update Rhino to make it work.
Okay, so like the package worked fine for you.
Okay, and
okay,
others.
I will redo that. Thank you. So it must be something with my machine. I'm going to restart and see what happens.
Okay.
Thank you.
Okay, you're welcome. Okay, no problem. Okay, for the third input is the distance method. So usually you can actually after 3, which is the 3 is the Euclidean distance, the squared Euclidean distance. Then you can add more. Any of these numbers means a square Euclidean distance. Only 0 or 1 or 2 or 3. This the 0 or 1 or 2 is the other methods. For C, it's the output classes. You need to define a kind of a class. Maybe this class is usually now it's a number, but maybe you can change it later. It's a 0 and 1 and 2. It's a class of red or green or blue, or cats, dogs, and cars. You can define it like this, but now we represent it as a number. And usually the class should be the same amount with the data. So now I have 9 data examples. So then I have 9 classes, not 9 classes, 9 items. Maybe they are only 3 classes. So I have only 3 in this example. And then K is how many neighbors to decide. So let's say in the last example, it was only 1. I only asked it what is the nearest, and I behave like this one. But maybe you need to increase this range. If you ask this one, and this is the nearest, maybe it's this is class 0, so then it says yes, I'm also 0. But if you increased this one, let's say into 3, maybe you find 2 points of this class 1 and 1 with class 0. Then you need to know how to decide, and it depends on the distances. So maybe you see visually, yeah, this is near, and this is according to, let's say, the Euclidean distance. But if you, from the next time we will discuss the other distances, you will find that maybe it's different. That, yeah, maybe this one is near to my question, so it should take a kind of a higher weight. So this is how many neighbors, okay? And of course, it depends on how many elements. So if you increase this K more than this, it will be red, because the error that you asked for too much neighbors. So let's say 0 or 1 or 2. Usually it depends actually on the data. If you have, let's say, million of data points, then maybe you need to ask a class with maybe thousands. If you have a very few data, so maybe 1, 2, 3 is enough. Okay, for this. And we will find now the impact of this. So now it's data. They call it, let's say, the training data. This is what we call in machine learning. And this is the testing data. And here is the machine learning algorithm. This is a supervised learning algorithm, because you have the data and you have the class. So this is a classification problem that we tackle. And here, the last piece, this is just for a representation. I will highlight this now. This to highlight the classes. You can follow these kind of things if you need, and we discuss it. If someone didn't understand any of this, we will discuss this in details. But this is mainly the classes. Only you have classes 0 or 1 and 2, and this is to highlight each one. Class 0 is white, red, and blue for the other classes. This just to color your points, or one point or many, with the class. This is I think this is the size, this one, and this is yeah, this is just to tell you the end of class. So maybe in the previous one, the output is not this kind of numbers. No, the output is mainly was this. Okay, it's a group. I need to get a specific item with all of its details as a text or lines. This one. Now we define this according. I will remove this one. Now let's see if we changed the how many neighbors to decide. So this was 2 according to those. What if we increase this to 2? And let's say now we will use the Euclidean distance, which is 3 or more. So this is 2. This is for the 3rd, 4th, 5th. It means that, yeah, this is the weights of these three is very high. So let's start to move this one. Okay, let's just have something unclear situations at this one. Okay, now it's 0 is with the 3. If we increase this to more, it's the same. So maybe it's hard to define this with within these elements. So let's just now add more data. Okay, now you will find, instead of just 1 point, then you will find this kind of patterns. So let's start from 1 or 2. This is 1, and this these outputs means that each point of this grid measure the distances for all of your data, and the distance now is this Euclidean distance. And according to now it's the only one, so this means that this after measuring all of the distances, it only behave like the nearest one. And if you started to increase this means that it will take into account the other weights, and usually it's like this. So now you have, let's say, 1 point, and you want to, let's say, these two is one class, and this is the second class. To define the output after reading the neighbor within these 3, so you calculate the distances from your point to others, then the points with the same class, you add their distances. So this gives it gives their class higher weight than 1 point from the other one. Then usually, so let's say I will do it now just to quickly. Okay, this is set 1 point, and this. Okay, let's say this set multiple points, and this is another one, just to describe it like this. Okay, so now you read just the distance between those and between this. So this is within these 3 nearest neighbors. So you add those. So now you have these. You add them, same as addition. Okay, and this is the distance. So the addition here is, say, 2.8, and this is 2.3. So now let's say we will put them on one list just to see it. So these are the collection for the class of these 2 points, and this is for 1 point. Usually they invert the. There is many ways actually. You can divide. Division. You can divide 1 over this data. So then it's easily you can find what is the nearest. You can get the higher. Okay, so it's just adding weights. Okay, and now you see how this, if you change it, the distances method. Let's say this is the Hamming distance, which is like a binary. It's see these vectors just 0 and 1. This is the cosine, and with this cosine, it's you only look into the vector directionality and not the magnitude itself. And we will see why each one depends on your kinds of data. This is the Manhattan distance, or this kind of a city cap. They call it also city cap, which you do not calculate this direct distance. You adding the weights of the grids, the distances of the grids. So we will describe each of these from the next time. But now you can find how much is the difference in the results for each of these points. So say it's in which class, maybe it's you see here this kind of outputs. Maybe from visual points of view, it's maybe it's nonsense, because usually you think about it like maybe something like this, but you have to say why this is, why you have this kind of two regions within these classes. So you have to calculate this kind of weights. With one, this is similar to Voronoi. It's the same idea. If you can use this Voronoi. One moment, someone asked, is it correct to say that in this example, the algorithm is increasing our experience knowledge by adding much more data than we could experience in real life? This is the question of Veronica. Increasing experience knowledge. Yeah, maybe this word, these two words is okay. What kind of knowledge do you mean? Because at the moment we usually we only use a two-dimensional in this example, only two dimension to decide what kind of class. But with the real life, the experience of real life, it's much more complex. So it's I still didn't get why you put this together. But yeah, this gives you a kind of an overview about that maybe in your real life you have a kind of you change your decision. Let's say your decision is a class. You change your decision according to how many factors you have in your thinking. You can build this kind of analogy. Yeah, I think so. So whenever you're adding more complex, more features, and you try to balance with all of these weights, maybe you are near to someone else within the same situation, but you behave differently. And this maybe means why it's very complex when you go into discuss something like humans, that if you have something hidden features that you were not able to see it physically. So with non-physical features, it's very hard. It's more hard. With the physical features, already there is a complexity because how to featureize and how to say that this is far or near to the situation. So this is just a discussion according to a Veronica question. What I was doing here. Voronoi, I remember. So now I will unhide the points. Here it is, and set multiple points. You can click here, Voronoi. Okay, and I will hide these outputs. And also these inputs. Okay, so this is with the Voronoi, and this means that any point within this region, this point is the nearest one. Okay, this is very simple, and but this is built geometrically, not algebraically, because with algebraically it's yeah, to replace it to geometry, to define a kind of a very clear edges, it's computationally not easy. So this, and I will give you another expression that this is maybe similar to the cones. Maybe you, if we, yeah, I think we can build another one here. This is easier. If we build different kind of cones, if these cones, all of them has the same height, let's say rendered and maybe top. Okay, so this the Voronoi example, and you can think about it like a weight, and you can think about this the height of these cones are the weights. Now all of them has the same weight. If you change it, the weight of anyone, so let's say I will do a scale in, let's say, 2-dimensional. Okay, so now this is the change only of the radius. Okay, if you looked from the top, so now, yeah, maybe you are within this, but you have bigger base. If you change the height, say with front, say scale 1 dimension, you will start to find these kind of curves, because they change, and this kind of things. So you can, this is one of the geometrical expression for this distances and weights. Okay, this is wireframe, and this is maybe tells you why so now, of course, this collect all of these two together. So with the Voronoi, maybe you saw subregions. So this is for the whole zero class, and if you change it, the movement of any of these, okay, so this is still this similar to Voronoi. Now let's just change. So this is the nearest neighbor. With the nearest neighbor, it doesn't matter a lot between the Euclidean distance and the city cap or the Manhattan. But if you started to increase this, so this increase this kind of weights, and this is very similar to what's happening with this. This means, let's say that you have a 3 cones from the same class has a higher weight, something like this. Now all of these kind of classes develops. By this we actually finished. Just I will mention that now we have only a 2-dimension to represent, but what if we use the same component like this, but with a multi-dimensional vector? Now we will find another problem that it's not easy to visualize. So you can get more than this kind of dimension. Now they are only 3. If we took something like those features, which is, one moment, I think, yeah, I think this one, I will take copy. And the other one here is paste. Okay. And maybe this is one of the challenges. Okay, so now, yeah, this one is the class, which is the last branch. These ones, and the features should be all of these. So let's say, yeah, and of course we need to this kind of description we have to change it to values. So now you have to know exactly how to deconstruct this kind of features as a text or as or this kind of words and values, and then you reconnect them. So I will explain a couple of components that you should use these components. So here mainly this one. So this for each feature, for each element. So maybe you need to remove all of the sixth value. So you can use also this cal. And let's say I will remove the sixth. Here it is. Okay, now I remove them. And maybe also I don't need the index because it's already according to its value. So I will also remove the 0, shift, and this one. So then I removed 2. For item, also you need maybe to select item 6 that you already removed. This one is this one, and you think how to change this, let's say, word vector. This is Boolean. We only use at the moment, oh, sorry, not this, Boolean toggle, this one. Okay, so now this is the values. This is strange, one moment. Should be all of them. Maybe because they, sorry. Yeah, for this one, we need just to make them flatten, because it should take all of the texts. Then you make this partition. Then you finish. Now you have, let's say, 9. And this is all of the features, 111, 101. So just remember that you need to make the inputs of all of the text all at once in a flattened image, in a flattened list. This is 1. This is if you need to how many words you can count. So then I increase this for more. So then started one of these words counted more than 1 and 0 and 2. So this is only to prepare this to join the others. Okay, and remember here that with this input, the input is not like that. You need to join. This is usually we will use it with these components. Join the text. And the connector is this, commas. Okay, now you have those. This is flatten. Now you need to merge these with I think with those. Yeah, this also needs this text. So these were the values without the index. And this one is this. You can, yeah, you can merge with many ways. Yeah, if you know, of course, programming, all of this can be done in a couple of fewer steps. With these components called AND, just double click AND, or this one, here it is. And the connection is also the commas. If you add these, then this means that this is the whole feature vector. And I just changed the features. The last one is it changed. Now this is the feature that I need to use. Okay, and for this index, this y, this should be your question. And from here, we will start to discuss what kind of features you developed, how many, what kind of drawings. And this is especially for the next time, because at the moment, we only able to visualize only two-dimensional outputs.